But this is where we left off with chapter 17. So again, carboxylic acids. So what happens when we do reduction reactions? So remember that reduction is a gain of hydrogen. Okay, so for carboxyl groups, that's actually a bit difficult to do. Carboxylic acids tend to resist reduction. So most of the reagents that we learned so far, like the catalytic reduction, right, H2 with a metal catalyst like platinum, palladium, nickel, that does not work on carboxyl groups. Okay, the sodium boryl tetrahydride also does not work. Okay, so really the reagent, if you're looking to reduce a carboxyl group, is the lithium aluminum tetrahydride. So the reaction is shown here. Okay, and what happens is the carboxyl group becomes an alcohol, a primary alcohol to be precise, since the carboxyl is at a terminal carbon. Okay, so you see that it's the lithium aluminum tetrahydride in ether. Okay, remember that this reacts violently with water. So you do have to do that without water. And then as a second step, we add water separately, okay, in order to get the hydrogen required for your alcohol. So it's a two-step reaction. The lithium aluminum tetrahydride in ether, okay, and then a second step, okay, which is adding the water. So this is really, again, if you're looking at the carboxyl, so why would you think it's so difficult? So these are bases, right? So what kind of reaction would you expect would happen between a carboxylic acid and a base? Right? An acid-base reaction, right? A proton transfer. So instead of leading to a reduction, a lot of these reactions end up leading to the salt plus water, right? An acid-base type reaction. And that's the reason you have to use a specific base to do this, because most are going to give you that side reaction. And so the nice thing is that because the carboxyl is so resistant, it's often not affected by, right, any of these other reagents that we've learned for reduction. So let's say that we had 5-oxohexanoic acid, right, we do the catalytic reduction here. Only the ketone is going to be reduced. Nothing is going to happen to the carboxyl group. Okay, same thing with the sodium boryl tetrahydride. Okay, again, right, you have here 5-oxo, 5-phenylpentanoic acid. Only the ketone gets reduced, right? Nothing happens to the carboxyl. So you know, it's a nice thing because, right, if you want to reduce just the carboxyl or just the ketone, you can choose the right reagents for that. So remember, that's called selective reduction. So if you get a question like that, it's really asking you to think about which reagent should you choose, okay, depending on what product you're looking to make. Okay. All right, so what other kinds of reactions can carboxylic acids do? Well, a very common reaction is known as Fischer esterification. So esterification means that you're making esters. Okay, and so this is probably the most common reaction. It is not the only way of making esters, but this is a very common one. And you basically take the carboxylic acid, so ethanoic or acetic acid here, okay, plus an alcohol, in this case is ethanol, okay, and then you have to add a catalyst, and it's an acid catalyst that works best for this reaction. Okay, so basically it's an acid catalyzed esterification. There are mechanisms for a base catalyzed, but the Fischer always works, okay, best with an acid, and in particular, sulfuric acid, phosphoric works well as well. Okay, but and then what you get is an ester, right? So the ester has the double bond O, but instead of an H, it has now a carbon chain, and that carbon chain comes from your alcohol. Okay, so basically what we're doing, right, removing an OH from the acid, removing the hydrogen from the alcohol, right, that makes water, Okay, and then you're combining the O, right, which is going to be your nucleophile, to your carbonyl. Does that make sense? And so the new bond is this one, right, between the oxygen and the carbon of the carbonyl. Does that make sense? Okay, so this is called an esterification, Fischer esterification reaction.
And just to clarify, an ester is an R.
So it's an R, C double bond O, O, and then an R on the other side. Right? So it's an O, and then the other side is also an R. So that H, right, of the carboxylic acid, that's replaced by a carbon chain. And again, it happens, right, by removing water. Okay, so it always makes, the Fischer esterification always makes an ester plus water. That's always the case. But there's a few issues with this reaction. So even though it's really common, this reaction is actually an equilibrium reaction or near equilibrium reaction, which means that it is actually not that favorable to make products, because what happens is as it goes forward, it goes right back. So it's an equilibrium with its reverse reaction. So it's not really a high yield reaction, and that's a problem, okay? But there's ways around that, okay? So if you want to make the product at high yields, right, if we think of Le Chatelier's principle, if our goal is to make product, right, maybe we can remove one of the products. And wouldn't it be convenient to be able to remove water? Okay, and that's really what this equipment does here, right? So what does this equilibrium means, right? The reverse, the forward and reverse reaction are going at the same rate, or nearly the same rate. And so a way to get around this is to actually get rid of water, okay? And so to do so, we use this piece of glassware here, which is called the Dean Stark trap, okay? And so what ends up happening is that you're able to remove water over here. So this kind of looks like what? A burette bottom, right? Like a piece of the burette, okay? And you would have your right vial attached here. You know that this is being heated, right? And so what's going to happen to the water?
It's going to go up.
Right? And then it's going to cool and fall back down as a liquid. Does that make sense? So it gets strapped on this side. So that's why it's called a trap. Okay, so this is also known as azeotropic distillation. So mouthful there. So that's, you know, a glassware that we would use, right, if we were attempting to do this Fischer esterification reaction. Again, to maximize, right, our product production, we can remove one of the products, and that means that the reaction goes, right, to the right. Okay, of course, if your acid and alcohol are inexpensive, you can always increase the amounts of the starting material. That also shifts the, right, reaction towards product. Again, Le Chatelier's principle dictates that that happens. So there's other things you can do, but often, right, you don't want to spend a lot of money having, right, bulk amounts of your starting material. So this is a nice and expensive way to do that, removing the water. Okay, so this is Fischer esterification. So the product is an ester, and this comes from, right, getting the attack here is going to happen, right? So this is going to attack, open, right? So you're going to get that tetrahedral intermediate. Okay, of course, this is done in an acid environment, so the first step is really for the protonation of the oxygen here, which when it attacks and opens, it would look like this, right, already, because the acid would have protonated the oxygen. And so you get that tetrahedral, so this R, right, the OH, and then what you're adding new, right? Does that make sense? So that's your tetrahedral. And then, of course, all you would need to do is to remove a hydrogen from here, right, as a final step, so deprotonation at the end. And, of course, that would give you the water. So that's the mechanism, or the intermediate, right, at the center of this mechanism. In that, with the Fischer esterification, you can really make a variety of different esters, because it really right, is a combination of an acid and alcohol. So whatever combination you decide to do, right, you can get a variety of different products. But let's say you just wanted to get the methyl version. So just adding a methyl here. So this R over here is always a CH3. Okay, there's a reaction for that, and that's done with diazomethane, so CH2N2. Okay, and so this is the diazomethane and its resonance structure. Now keep in mind this is potentially explosive, toxic, it's a yellow gas, so it's pretty nasty to work with. But when you get, right, this resonance here, it allows you to transfer just the carbon. Okay, and so what you end up with is a methyl ester, just the CH3. And so this is the mechanism. So remember over here you're doing, right, a resonance, so you'll take the one with the carbanion for the first step. See, the carbanion is going to come in, right, act as a base, remove the hydrogen, okay, and then those electrons will go back on the oxygen, so you'll have your carboxylate ion plus this methyl diazonium cation, and then that will go on to the second step where you will attack, and like I said, you can just pick up the CH3, right, and then the bond between the carbon and the nitrogen is broken, and then you just get nitrogen gas, right, N2 as a side product, right? And this is an SN2 mechanism, so nucleophile attacks, leaving group leaves, and you have your product. But again, this has a limitation, right? You only make a methyl ester. So if you want a variety, this isn't going to be the method for you. But, okay, if you want the methyl ester, then this will work. Right? So another reaction that you can do with carboxylic acid that's really useful is converting your carboxylic acid to an acid chloride. So basically what's happening is the OH is now replaced by a halogen. So these are actually, as a class, acid halides. So you can have chlorine, bromine, iodine. But the most common version is the one with the chlorine. Okay, so acid chlorides are the ones we're going to be dealing with in this class. Okay. And so naming, what you use is the name of the acid. So this would be called acetic acid, right? 2 carbons. Okay, and then what you do is you make that a substituent name, so acetyl, right? And then you add in chloride for the chlorine, so acetyl chloride, right? This could be phenyl, right, chloride, but the problem is there's a carbon out here. So a carbon plus the benzene, it's called a benzoyl, so that's where you get that name here. So, and then of course chloride is for the chlorine. Okay, and we'll do more naming on these next chapter because we'll deal with acid chlorides then. So we'll do some more naming, but just giving you an idea here where those names come in. So how are these prepared? So of course you start with the carboxylic acid, and what you're going to add is thionyl chloride. And we've seen thionyl chloride before as a way of, right, using the chlorine as a nucleophile. So that's a common reagent for that. But here it's going to function as a way of adding the chlorine to the carbonyl. And again, you're getting rid of an H, right? Or I'm sorry, you're getting rid of the OH, okay? And so you can see that you gain an oxygen as part of the SO2, and then the hydrogen comes with the H, right here, HCl. So sulfur dioxide and hydrochloric acid as side products. And so this again, mechanism for this. So remember that the goal here is to transfer this chlorosulfite group. So these are, that's really the goal here. So this is thionyl chloride, right, over here. And you're making that leaving group, right, a good leaving group. This is not that great. So we're trying to convert it into something that is good. And then the Cl can come in, right, and attack. Does that make sense? So you're converting the OH to this chlorosulfite group. That's the first step. and then the chloride ion acts as the nucleophile, right, attacks, opens, and then this closes, because you do get that back, so you see that in this intermediate, this closes, and then the leaving group leaves, okay? And of course, again, it leaves as SO2, right, and then the Cl minus, which is going to pick up a hydrogen, okay, to make HCl. So that's the acid chloride. So that's really, again, really common reaction, and we'll do more on that on chapter 18. Okay, or what do we do when we have these acid chlorides? And then lastly, the last reactions that are important for carboxylic acids are called decarboxylation. So basically what we're doing here is getting rid of a CO2, a carbon dioxide molecule. Okay, so if we look at, right, the structure, just a general structure of a carboxylic acid, you see the CO2 right there in the center of it, right? So this is really what is going to leave, right? And again, as a carbon dioxide molecule. And then what's left is the R with the H, so just the carbon chain. Okay, this requires heat, so it's often called thermal decarboxylation. So it requires that you heat. Okay, now the problem with this is most carboxylic acids, they actually will melt or even boil before you reach enough heat in order to get this reaction to go. So this does not work for every carboxylic acid. Okay, it works for the carboxylic acids that have a ketone, yeah, beta ketone. So not a ketone right next to it, but a ketone, right, 2 carbons over at position 3, right? 1, 2, 3.
Is that because it increases boiling point?
So what happens is that it's actually going to allow for a resonance to happen here. So this is a very reactive place, this alpha position right here between 2 carbonyls. So, and that's going to be key for chapter 19 also, these beta keto acids. That's what we call beta, right? Keto, ketone, acid. So that's really where the decarboxylation will come into play in chapter 19. Okay, so under warm conditions, so you don't even have to heat it up really high when you have that beta keto group. Okay, what happens again is you're able to get rid of, right, what's in yellow here, which is the CO2, right, as carbon dioxide. And then you're left with, right, these carbons here. And of course the beta carbonyl group. And of course that H gets incorporated with the alpha carbon. So these thermal decarboxylation are specific to beta keto acids. And again, we'll spend a lot more time on this on chapter 19, but it's an important reaction. And this happens a lot in biological systems. That's how we produce CO2 during the Krebs cycle, for instance, or the citric acid cycle. And at the heart of this is this 6-electron cyclic structure here that forms as a transition state. So it's, you can see here, it's not connected per se, but you can see how it's 6 members, right? 1, 2, 3, 4, 5, and the hydrogen makes 6. And they're all, right, interacting in some way here with these shifts. Right? So you see that the double bond picks up the hydrogen, right? The electrons here make the double bond, and then it breaks this bond, which releases the CO2. Does that make sense? So you can kind of see how this is possible, and it wouldn't be possible if you didn't have this keto group over here. Okay? And so again, this position right here is really important in lots of different organic chemistry reactions. So again, you release the CO2, and then you're left with the enol, but we know the enol tautomerizes back to the ketone. So the product is the CO2 plus acetone in this case. So again, this is really only going to happen for these beta keto esters, but a number of biologically relevant acids have that. function. And for instance, oxalosuccinic acid, okay, it's part of the citric acid cycle, and you can see that it has that, right, carboxylic group alpha beta to a keto, right? And so this is one of the reactions that is a decarboxylation reaction in the citric acid cycle, okay, and it makes alpha ketobutyric acid. So that's the thermal decarboxylation, and it happens anywhere that there's that, again, beta position. So it could be two acids. Doesn't have to be just a ketone over here. It just has to have the double bond O. So it could actually be a dioic acid, right, or malonic acid, okay, malonate, or malate, excuse me, is also something that we see, again, in chapter 19. And again, it does require heating for this, but you release the CO2. And notice that you don't release both, just one at a time. Okay? So that's something else we'll stress once we get to chapter 19. But that's really, again, just showing you the mechanism between the two acids. So again, it's that 6-membered ring that's making this possible, right? The double bond gets the hydrogen, right? The electrons here make the double bond for the CO2, and then you release the CO2 by breaking this carbon-carbon bond here to make the enol. And then the enol tautomerises back, right? So you get the carboxylic plus the CO2. Does that make sense? And malonic acids, okay, malonate, we're going to talk a lot more about that in 19. So we'll leave it at that. And that's it for 17. Yes, sir. Is that for that homework problem? Yes, I'll come before we finish. Any other questions on 17? All right, so again, if you do want additional time on now, please shoot me an email and I can open it up for another day or two. Okay, so just let me know. Thank you.